The image you see represents the popular idea of a protective force field around a spacecraft, which is a concept often used in movies and books. We will take a deeper dive into how electric fields actually function and their applications in the real world. In many movies and video games, force fields are shown as glowing walls or bubbles that physically block objects like lasers, bullets, or ships. These force fields work by requiring actual contact to stop an attack, acting just like a solid barrier. This portrayal makes the force field behave as if it were a tangible, solid object, even though it's meant to be an energy-based barrier. In physics, a field isn't a physical barrier, but a property of space that lets objects influence each other without touching, which we call a non-contact force. For example, the gravitational field allows masses to attract each other, as shown by the Earth pulling objects toward it. Magnetic fields arise from the interaction between poles of magnets, like the north and south poles on a bar magnet aligning with a nail placed nearby. Similarly, electrostatic fields occur between charges, such as two positive charges repelling each other or attracting when opposite. These fields extend through space, creating invisible connections that explain how forces can act over a distance without direct contact. Next, we'll look at how physicists represent fields that can't be seen directly. They use vectors, which are arrows that show two important things about the field at any point: the direction the force is pushing or pulling, and how strong that force is. The direction is shown by where the arrow points, and the strength is shown by how long the arrow is. This way, even though the field itself is invisible, we can understand its behavior by looking at these vectors. The image here illustrates this by showing arrows radiating outward, indicating forces pushing away from a central point. This helps us visualize how the force varies in both direction and magnitude around that point. Here, we use continuous field lines to represent the strength of a field instead of drawing many individual arrows. The key idea is that the strength depends on how closely packed these lines are in a certain area. For example, in one section, the lines are very close together, indicating a stronger field, while in another section, the lines are more spread apart, showing a weaker field. This method makes it easier to understand and visualize the field's strength at different points without cluttering the image with too many arrows. Now, let's talk about the electric field. It's the area around a charged particle where another charged particle feels a force without touching it. The charge that creates this effect is called the source charge, labeled as Q. This source charge changes the space around it, creating what we call an electric field, which influences other charges nearby. To measure the strength of an electric field at a certain point, physicists use a concept called a test charge. This test charge is a small positive charge placed at the location where the field is being measured. It has to be positive, so the direction of the field lines matches the direction the test charge would move if pushed. Also, the test charge must be extremely small, so it doesn't create its own electric field that could interfere with the measurement of the source charge's field. This way, the test charge helps us understand the exact strength and direction of the original electric field without altering it. Let's take a closer look at how electric field strength is defined. It's calculated as the force experienced by a charge placed in the field divided by the magnitude of that charge. Specifically, the electric field strength, represented by E, is the force, F, measured in newtons, acting on the test charge, Q, divided by the size of that charge, which is measured in coulombs. So, the electric field strength tells us how strong the field is based on the force per unit charge at a given point. This fundamental relationship helps us understand and predict the behavior of charges in electric fields. Now, let's look at the radial field equation, which describes how the electric field from a single point charge spreads out in all directions in three-dimensional space. When you combine the relationship of electric field as force over charge with Coulomb's law, it gives a formula showing that the electric field strength decreases with the square of the distance from the charge. This means the further you move away, the weaker the field becomes, following an inverse square law. Mathematically, the field strength E equals a constant K times the charge Q divided by the distance r squared. The constant K is a well-known value in physics that helps quantify this relationship. On the right, you can see a graph illustrating this drop-off, where the field starts strong near the charge, then quickly decreases as the distance grows. This idea helps us understand how forces behave in space around charges. When dealing with charged spheres in physics, such as those found in devices like a Van de Graaff generator, it's important to understand how to simplify the problem. Instead of considering the charge spread across the surface, you model the entire charge as if it's concentrated at the very center of the sphere. This means that when calculating forces or fields, you should measure the distance from the center of the sphere to the point of interest, not from the surface. For example, if the sphere has a radius r and the point is at a distance d from the surface, the total distance r you use in calculations is the sum of these two, r plus d. This approach helps simplify the math without losing accuracy in real-world physics problems. Here, we have a point charge with a given magnitude, and we want to find the electric field strength at a specific distance from this charge. The diagram shows the charge as a circle labeled Q, with a magnitude of 5.0 microcoulombs, and the point where we want to find the electric field is 0.3 meters away. This sets up our problem in the physical world. Next, we will move on to the mathematical side to figure out how to calculate the electric field strength at that distance using the appropriate formulas and constants. To solve this, we start by identifying the relevant equation for the electric field, which is E equals K times Q divided by r squared. Next, we substitute the given values into the formula. K is 8.99 times 10 to the 9th, Q is 5.0 times 10 to the minus 6, and the distance is 0.3 meters. We then calculate E equals 44,950 divided by 0.09. The electric field strength we found is approximately 4.99 times 10 to the power of 5 newtons per coulomb. Let's look at an example involving an electron placed in a uniform electric field. The field strength is given as 2.0 times 10 to the 4 newtons per coulomb, and we want to find both the magnitude and direction of the force acting on the electron. We know the charge of an electron is negative 1.6 times 10 to the negative 19 coulombs. In the physical world diagram, the electric field vectors are pointing upward. Since the electron has a negative charge, the force it experiences will be opposite to the direction of the field. So, the force on the electron will be downward. We start with the equation that relates the electric field to the force and charge, which is E equals F divided by Q. By rearranging this equation, we express the force as the product of the charge and the electric field, or F equals QE. Next, we substitute the given values into this equation. We take the magnitude of the electron's charge, which is 1.6 times 10 to the minus 19 coulombs, and multiply it by the electric field strength, 2 times 10 to the 4 newtons per coulomb. Multiplying these gives us a force magnitude of 3.2 times 10 to the negative 15th newtons. Because the electron has a negative charge, the force will act in the direction opposite to the electric field. So, although the field points upward, the force on the electron is directed downward. Let's move on and review a more advanced example where we need to find the exact distance from charge A at which the net electric field is 0. We have two positive charges, one with plus 4 microcoulombs and the other with plus 9 microcoulombs, placed 1 meter apart. Our goal is to determine where the effects of these two fields cancel each other out. Imagine a point along the line between the charges. We assign the variable x to the distance from charge A to this point. The remaining distance to charge B is then 1 minus x. By balancing the magnitudes of the electric fields from each charge at this point, we can solve for x and understand the influence each charge exerts in space. When the net electric field is zero at a point between two charges, it means the electric forces from both charges cancel each other out perfectly. This balance point depends on the magnitudes of the charges and their separation distance. Mathematically, this means the electric field from A, which is K times the charge Q underscore A divided by the square of the distance R underscore A, equals the field from B, K times Q underscore B over R underscore B squared. In the diagram, you can see point P between the two charges, with electric field vectors pointing away from each charge but in opposite directions, indicating they cancel at point P. This equality sets up the equation we use to find the specific location where the fields balance out perfectly. By taking the square root of both sides, we can solve for the distance where these fields balance perfectly, allowing us to determine the exact point where the net electric field is zero. Taking the square root of both sides, we simplify it to 2 over x equals 3 over 1 minus x. Multiplying both sides by the denominators results in 2 times 1 minus x equals 3x, which we can solve further to find the specific location of point P where the fields cancel each other perfectly. This leads us to the equation 2 over x equals 3 over 1 minus x. From there, we multiply both sides appropriately to clear the denominators, giving us 2 times 1 minus x equals 3 times x. Simplifying this results in 2 minus 2x equal to 3x. And solving for x, we find that x equals 0.4 meters. Let's continue by looking at the relationship between the charges and distances in the physical setup. We have two charges, one with plus 4 microcoulombs and the other plus 9 microcoulombs, separated by 1 meter. Our goal is to find the point P where the electric field from both charges balances out, meaning their influences cancel each other. By setting up the equation with the constants and distances squared in the denominators, we can solve for x, the distance from the first charge to point P. Taking the square roots simplifies the fractions, and rearranging terms leads us to the final solution, showing that point P is 0.4 meters from the 4 microcoulombs charge. This gives a clear connection between the math and physical scenario, helping us understand where the fields cancel in this setup. If you found this material helpful, I encourage you to check out physicsib.com. It offers a well-organized and interactive course that can support your learning further. Whether you want to deepen your understanding or follow a structured path through the topics, this resource is designed to guide you step by step. It's a great way to build on what we've covered and keep progressing with clear explanations and practice opportunities. If you found this presentation helpful, please take a moment to like and subscribe for more content like this. For a more structured and interactive learning experience, visit physicsib.com, where you can explore courses designed to support your studies. Thanks for watching, and see you there.